What is the ultimate metric? Well, what if we imagined the dream organization? So Jean Kim this morning talked about this idea of the unicorn project and these 5 ideals. If we thought about what are we trying to aim for in a great organization? What does this vision look like? Or if we shrunk the scope a little bit, what if we imagined the dream team? What kind of team do we want? What does this vision look like? So several years ago, I read this book, The 5th Discipline, The Art and Practice of the Learning Organization by Peter Senge, one of the most inspiring books I've ever read, about this vision of what it means to be a great organization and the scientific rigor in organizational learning. Has anybody read this book? A few people. Everyone else, add this to your reading list. So this book is pretty old, though. It was written in 1990, but tons of great ideas in here. And with great ideas, this deserves some modernization. So in this talk, I'm going to focus on how do we do science in software development. And that's really what this talk is about, the ultimate metric. So first, what problem are we trying to solve? That's always a good place to start, right? What's the strategy for solving these problems? Then what is the ultimate metric? And then we'll talk about how do we do science with paper and pencil. All right, first, what problem are we trying to solve? So the real problem I think we're really trying to solve here is pain, this misery in our jobs that makes us want to run away from all this suffering we deal with at our work. But when we try and talk about pain to our management and our business leaders, they're like, why should I care about pain, right? Suck it up. So why should we care about pain? So across the industry, we see this pattern where every few years we end up rewriting our software after driving one project after another into the ground. And we always start off with the best of intentions, right? We're going to write high quality code that's low in technical debt, easy to maintain, and of course it's got to have good code coverage. And then this happens. And we've got this business pressure and constant urgency, and things just start to unravel. And the problems escalate in these stages. So things start off okay, but our problems are invisible. They're hard to measure, hard to explain, and there's all these features to build and not enough time. And so we bring up our concerns to our product owner, but our product owner's like, we've got more important things to do, right? And so we keep deferring the problems. And then as the problems grow even further, the releases start to get painful and chaotic, and we'll be down to the wire, and the software will be broken. So we start working late nights and weekends to get the software back into a shippable state. And then we start relying on all these high-risk heroics to keep saving the day. And then instead of our management seeing all this chaos as evidence of our problems, we're congratulated for our all-nighters and our great teamwork. Good job, everyone. Keep up that great work ethic, right? And then as the problems grow even further, productivity slows to a crawl, and the builds will be breaking, and environments are going down, and nothing gets done without pain. And so we start pleading with our management to give us time to fix all these problems, but now we're even further behind on our commitments, right? And so our management's in a panic. They're like, we need to go faster. Let's hire more developers because that'll fix the problem. And so now we've got developers breaking things because they don't know the software. And it becomes a full-time job just to keep the project from falling apart. And eventually exhaustion sets in, and that's the tipping point for project meltdown. And there's usually one last-ditch effort by the team to turn things around. But if management says no, and the team loses hope, that's like the final nail in the coffin, and the developers just start leaving in droves. I give up. I don't even care anymore if this project fails. And most projects at this point will never recover. So who's been here? Anyone? Anyone been through this cycle, right? This is the pattern in our industry that we repeat over and over and over again. So what's wrong with our current strategy? You know, it's not like we don't know that it's important to write maintainable code, right? We've been talking about these things for years. So what's wrong with our strategy? So I was reading this book, Good Strategy, Bad Strategy. And by the first chapter, I already had an answer. A description of the goal is not a strategy. And if you think about it, what's our strategy for success? It's a description of the goal, right? We talk about what it means to write maintainable code and why these things matter. But what we don't talk about is how the hell we're actually supposed to pull this off in the context of a business. So the problem is we don't really have a strategy for solving these problems, and we really need one. So Rumelt says, a good strategy is a specific and coherent response to an approach for overcoming the obstacles to progress. So what are these obstacles that we need to overcome? And I think the number one obstacle that we need to solve is this communication breakdown between the management world and the engineering world. Where on one side, we've got visibility and no control. And on the other side, we've got control and no visibility. So what happens when we've got communication breakdown? Well, if we look at this from a systems perspective, let's imagine our organization for a minute was a robot. And our robot has an arm controller, a hand, and a pain sensor here, and we've got this communication breakdown between these two components. So what happens? So imagine that our organization is a robot driving a car, and planning is like aiming the car. See my keynote animation skills, pretty cool. Investment is pushing the gas pedal. And risk management is steering in response to emerging risks. And this is where we really fail, right? When these problems come up, we're not responding to that pain sensor, and so we just run the project into the wall. And our reality is more like an agile barge. And we're failing to learn from our mistakes. We do this over and over and over again. So what if we measured our pain? What would that look like? So if you imagine for a minute that we could measure these thermodynamics of our emotions and graph a little chart of our project over time. This is a stress wave over time. Early on in the project, this is where we have really happy engineers. And towards the end here, we're like running away from misery, right? What if we could make this visible? What if we could measure it? So what is this pain? What if we tried to put a definition on this? This is the one I came up with. Pain is a stress signal in our bodies that tells us we ought to move away from something. But the problem is we don't move, right? And why don't we move is this pain signal is lost in translation. And this is the problem that we need to solve, the obstacle that we need to find a way to overcome. So how do we do that? What's the strategy? So I want to tell you a little story from the trenches. This is the topic of my book, Idea Flow, How to Measure the Pain in Software Development, this journey of running into the wall and learning what to measure. So about 10 years ago, I was on this really great team, disciplined with best practices, constantly working on improvements. We had CI, unit testing, design reviews, code reviews, all the things, right? Like 85% unit test coverage. And despite all these things, I watched my project hit a wall. And by hit a wall, I mean we brought down production 3 times in a row and the project just kind of went off the rails. So we had a pretty typical Scrum process. We had these 4-week sprints. We were doing normal planning and release cycles and deploying to production. But why didn't this retro process that we have, driving all these improvements that we were doing, prevent us from hitting the wall? So if we think about these retrospectives we have, here's my team and our biggest problem over there, the elephant on the right. And we have this question like, what's the best opportunity for improvement that our Scrum Master would ask us? And we'd all come up with these ideas and brainstorm a big list. The awful email template engine code, or fill in missing unit tests, or we should clean up the database code, or let's improve maintainability of our test framework. Always wanting to make that test framework better. But here's the thing I learned. Just because a problem comes to mind doesn't mean it's an important problem to solve. And when we're asked a question like this, what's the best opportunity for improvement? And our brain doesn't really have a good way to come up with an answer. The question that our brain really answers is, what do I feel the most intensely about? And an answer comes to mind. And this is where all these different biases come into play. So for example, recency bias. So the problems that bothered us most recently are more likely to come to mind. Or guilt bias. If you've ever felt guilty about not writing those unit tests that you're supposed to write, you really, really, really want to solve that problem. Or known solution bias, where we're more likely to think of the problems we know how to solve as opposed to the problems we don't. Or sunk cost bias. Once we've sunk tons and tons of time into this test framework, we really want to make that work for us. And so what would happen, sprint after sprint, we work on all these improvements, but our improvements didn't end up making much difference. We spent tons of time working on improvements, but our choices without visibility kind of look like this. So here we are after this third production outage we had, talking about, okay, what are we supposed to do now? Right? We're doing all the right things. And I thought the problem was all this technical debt that was building up in the code base and causing us to make mistakes. And I was trying to convince my team of this, but they're like, well, why is your opinion any better than any of our opinions, right? They're just all opinions, right? Without data, you're just another person with an opinion. And so I started thinking, okay, well, how can I convince my team of this problem of technical debt causing our mistakes? And this was my hypothesis, right? Let's try and do a little science here. And so I wrote this tool that could detect high-risk changes in the code and let us know where we needed to do extra testing. And I used historical data from our defects in Jira compared to where those code changes were to try and prove this case that our biggest problems were coming from our high-tech debt code. But what I found wasn't what I expected at all. Most of our mistakes were actually in the most well-written parts of the code, as opposed to the code that was full of technical debt. And I kept trying to mangle the data, trying to make sense of it somehow to make this case for technical debt, but I couldn't actually do it. And this is what our code looked like. I was working on a statistical process control system in semiconductors. So we had the tools would send measurement data in, and it was our system's responsibility to set off an alarm if there was something wrong with it or determine if it was okay. And we were writing this rules engine that had a configuration UI and a charting UI on top. And our code kind of looked like this. The core engine was gold-plated by our most senior engineers and all factored well and unit and integration tests and all the things, right? And then the code on the periphery, we had all kinds of ugly, crazy stuff going on, and we had some like 5,000 line classes that made everyone cringe, and we all wanted to fix these things, right? But when I looked at the data of where our problems were actually coming from, most of the bugs were actually in that most well-written part of the system that was gold-plated, full of testing, and written by our most senior engineers. And I looked around, and I was trying to make sense of the patterns. And it was really difficult to try and find any correlation that had to do with these areas that we really wanted to fix. But the correlation I did find was this, and that we made significantly more mistakes in the code that we didn't write ourselves, and that lower familiarity increased the likeliness of mistakes more than any other factor. I couldn't help but think, though, there had to be more to the story than that. I mean, this is what I knew. When I had to work with complex code, it was really painful. But what makes development actually feel painful? And so to figure this out, I started keeping track of painful experiences with the code and visualizing them on a timeline like this. So the pain starts when I run into some unexpected behavior and ends when the problem is resolved. So this is 5 hours and 18 minutes of troubleshooting. Would all of you agree that's pretty painful? So this became a way for us to standardize our definition of pain. So these time bands here this time band is the time I spend confused, and I'm trying to resolve that confusion so I can get back to work. So what causes all this confusion? So if I wanted to understand the causes, you can think of the causes as being driven by risk factors. So the amount of confusion was caused by two factors: the likeliness of unexpected behavior, and then the cost to troubleshoot, repair the problems. And so as we started breaking down these specific examples, we started breaking them down into categories. And what I realized as we did this is most of the confusion was actually caused by human factors as opposed to problems inside the code itself. So for example, stale memory mistakes. So this is when I have an idea in my head about how the code is supposed to work, but it doesn't work that way anymore because somebody changed it. Or ambiguous clues. This is when you're running an experiment and there's multiple possibilities for how behavior can occur, and you make a bad assumption and down the rabbit hole you go troubleshooting for hours because you turned right instead of turning left, right? So these aren't really problems inside the code itself. Confusion occurs during this process of understanding and changing the software. Confusion is this emergent effect of these interactions. And so we started optimizing for what I call idea flow, this flow of ideas between the developer and the software, rather than optimizing the code itself. And we did that with the help of a data-driven feedback loop. And once we started looking at this data, you really started to see these different biases that come into play. So I mentioned this question of, what do I feel the most intensely about? And this comes up when we code too. So if you imagine a timeline, this is the time here that I'm running an experiment. Any experiment we run follows the same kind of pattern where we set up an experiment, we execute the experiment, then we analyze the results and decide what to do next, and then we do this over and over again until we solve the problem, right? And when we're executing something, we're waiting, and time feels like it goes really, really slow, and we're really annoyed because we have to wait for that test to finish, right? And when we're doing stuff, the time seems to zoom by, right? Because we're busy doing things. And so what happens in our bias is we're really annoyed by execution time. We really want to fix execution time, even if most of our time, multiple orders of magnitude more time is spent on human cycles, our bias is still toward execution time. Another case, you start realizing how our pain sensors are really quite terribly miscalibrated. So for example, ugliness in the code bothers us a lot. Lack of familiarity bothers us a lot. These things are like, oh, this is awful, I really want to fix that. But moderate difficulty is actually enjoyable. Now think about the effects of that a minute. When you finish a really hard problem and you solve that thing, are you like, oh, that was so awful and painful? No, you're like, all right, that was awesome. I solved that really hard problem, right? Like, these things are fun. We are professional problem solvers. We have fun doing this kind of stuff, right? Our pain sensors are really quite miscalibrated, but we can recalibrate our pain sensors with data. So my team had spent tons of time working on improvements that didn't make much difference. And we had tons of automation, but the automation wasn't catching our bugs. And we had well modularized code, but it was still extremely time consuming to troubleshoot all these defects. And then we started asking one key question. What are the specific examples of when we experienced this pain? We stopped having these conversations in terms of generalizations and started looking at the data, and that's when everything changed. And I learned one of the most valuable lessons of my career. The hard part isn't solving the problem, it's identifying the right problem to solve. The hard part isn't solving the problem, it's identifying the right problem to solve. So commit that one to memory, makes all the difference. So our strategy then became to use data to optimize flow and to focus on steering better and making a commitment to focus on the highest leverage 20% of the problems based on data. Made all the difference in the world in turning our project around. But what about this problem? This is a hard one, right? How do we solve this problem of communication breakdown? So the key insight for this actually came from this business coaching. I was in this MBA training class with a bunch of business folks that didn't really know anything about software. And I was explaining this whole problem of technical debt in the software world and how this builds up in the code base. And as I was explaining this to the business folks, the response was, oh, that doesn't sound so bad. I was like, what? You don't want to know what the interest rate is or anything? Really? Doesn't sound so bad? I can try and make it sound really bad, but they're like, no, I think that's okay, right? And the thing I learned is that business folks look at loans a lot differently than we do. Loans in the business world are a predictable financial tool. It's an instrument for achieving leverage. So in the business world, we've got this really cool way that we do math and make decisions. So we've got revenue minus cost equals profit, right? And then we start with a goal. Oh, I want to improve profit by 10%. And then we work backwards. There's only a handful of knobs you can turn, right? You can increase price, increase sales, or reduce costs, and then you come up with some investment strategy. I basically decide what buckets I'm going to put the money in. And the thing that I learned, what makes investment decisions harder isn't higher costs, it's lower predictability. So if I know I've got a predictable increase in cost over time for my software project, I can go, oh, well, that's all right. I'll just throw more sales money in it to compensate, and we'll be good, right? Don't reason about these problems quite right. And yet when you lose predictability, what happens is I try and put money in these buckets, and I can't make decisions. I can't run my business if I don't know what's going to happen when I stick money in the bucket, right? What makes investment decisions harder isn't higher costs, it's lower predictability. But that's exactly what's happening, right? Predictability on our software projects is going out the window. As difficulty approaches this cliff of the impossible, what is this cliff? It's a constraint, right? The ultimate constraint that we have here is our human limitations. Once we lose our ability to understand cause and effect, we lose our capability to deliver software. It's kind of a big deal, right? We're talking about the whole thing crashing and burning and going down in flames. It's not like a loan. And so this technical debt metaphor is really misleading when you don't actually understand the underlying mechanics and all you have is the metaphor to reason with. And we shouldn't make decisions at a business level in the same way that we'd make decisions with a loan. In these interest payments, this idea that we give management are not really loan-like at all. And so a better way I've found to explain this is in terms of escalating risk. And that when risk factors multiply, troubleshooting becomes too hard and predictability flies out the window. So the way I think about this is the thing that we need to change is our decision habits. And this confusion that we experience as a result of our decision habits. So for example, if I write a little code at a time, work out the kinks as I go, troubleshooting is usually fairly quick, right? This is why we try and work in these small iterations, and it's pretty easy to troubleshoot the problems. But what if I go, skip the tests, who needs tests, right? And often we end up with a big haystack of changes and troubleshooting becomes really hard, right? We rush the work to try and go faster and we're gambling, but often this is exactly what happens, right? It took us 3 times as long to do this thing because, we didn't take our time. Sometimes you gotta slow down to go faster, right? And so we can get in this habit of constant urgency and making these high-risk decisions. We get stuck in this cycle of chaos. So first there's constant urgency, which leads to this feeling of time pressure. Then we start compromising safety for speed, which increases the number and severity of these hazards we run into, which leads to more pain and higher task effort, which leads to more time pressure, and we get caught up in this vicious cycle. In this cycle of chaos, escalates risk. But we can also go in the opposite direction with this cycle of safety and get in the habit of low-risk decision into low-risk decision habits. So first, we stop and think, and then we come up with a strategy to mitigate the risk, which leads to fewer problems to fix, which leads to increased productivity and give us time to innovate. Now we've got time to stop and think, and you end up in a virtuous cycle in a similar sort of fashion. So this cycle of safety ends up reducing risk. So the way I think about this now is our software is actually a reflection of our decision habits, and our decisions are the things that ultimately are causing our pain. So if we get in this habit of making high-risk decisions, we get all these unmaintainable software problems as a result. And then if we rewrite our software, but don't fundamentally change the way we make decisions, our problems just keep coming back. And so we've been blaming technical debt for causing our problems, but technical debt is really a symptom of the problem. Or another way to say this, just because we repaired the car doesn't mean we learned how to drive. And we got to learn how to steer in response to those emerging risks. At some point, you're always going to hit that limit, and we need to learn how to respond in order to keep these projects in a sustainable pace. So how is this different? I want to break this down specifically, these two metaphors, technical debt or escalating risk. So with technical debt, we've got this predictable increase in cost over time, whereas with escalating risk, we've got a probabilistic model that captures this loss of predictability. With technical debt, you can add resources to compensate for this predictable increase in time. We all know it's a bad idea to add developers to a project that's fallen off the rails, right? It makes things worse. But in the old iron triangle sort of ways, doesn't make sense, doesn't quite connect. So with escalating risk, adding resources escalates risk. With technical debt, we've got this bias around problems being inside the code. We're trying to look for that debt-like thing to blame for our problems. But problems are really in these interactions, and they don't have to be nouns. But the metaphor biases us to nouns in our thinking. So this metaphor I found is actually quite misleading to management, and I think we should actually stop using it and instead explain it this way in terms of escalating risk instead. So strategy then is to create this shared language of risk that can work in the small and work in the large, and we can have a shared bridge language that makes sense at all levels as a shared thing that we pull towards. And then let each team steer their own project, have 20% of their capacity for making improvements. And this, you also notice I kind of flipped the organization over here. So now instead of our management having this command and control structure, we've got a collaborative support system that's about lifting up the teams. And from here, we can really start taking a lot of these ideas from the fifth discipline and applying them to our organizations and building a learning organization. And what this looks like, template-wise, is an organization that's built around innovation, based around creativity, love, and mastery. We're going to work together to build cool things for the world, right? Coming together to make the magic happen. All right. So what is the ultimate metric? So as I started working on this, I had this realization that when we map these metaphors from the lean world over to agile, this metaphorical mapping we made of this idea of the feature factory basically broke all the mathematics around control theory and how they were used in the manufacturing world. So I started wondering, since I had this background in statistical process control from the lean manufacturing world, is there a way that we can actually fix this math? And I started collaborating with my good friend Michael Feathers on a strategy to bring this scientific rigor to the world of software development by modeling anatomy of invisible systems with our engineering skills. And he made this really key realization. This is really important. So when you've got two systems with similar dynamics, system A and system B, and you can use A as a metaphor for B, and you can also use B as a metaphor for A, it says something about the mechanics of the underlying systems, that we can distill those similarities. And so we started working on distilling forms that characterize the similarities across systems in terms of explicit, structure, and forces. And he's got this book he's working on, Book of Forms, with 13 patterns of forms that you see in all of these different sorts of systems, and all kinds of things. So where do we see these patterns in our socio-technical systems? So if we start with this socio-technical human network, what are some systems with similar dynamics? Can start thinking about, well, distributed software networks kind of look like human communication networks, right? And these manufacturing process networks also kind of look like these similar networks. And so you start looking at all these parallels of these rhyming systems and distilling those patterns, distilling the things that we learn across these structure and forces, and can map and come up with new techniques. So what I was doing in my book is essentially mapping all these ideas from control theory to the world of software development and coming up with a strategy for doing flow control and steering capability and mapping all these ideas from the lean world over into software development. So, theory of constraints. Who's familiar with the theory of constraints? It's a good one to know. So, in the manufacturing world, if I've got a process with 3 steps, and here this process step in the middle is 2 units per hour, it's a little slower than the other ones, and the rate of flow at the bottleneck determines the rate of flow of the overall system. So if I want to make this whole system go faster, I need to focus on this limiting constraint. Well, what's the limiting constraint in software? And we talked about this a little bit earlier as this difficulty of work increases, we hit this wall, right? Well, what is this wall? This limiting constraint is human understanding. And when we think about theory of constraints, these are the type of constraints that we need to start thinking about. Is once we lose our ability to understand cause and effect, we lose our capability to deliver software. And we need to stay away from that cliff, right? Where costs are just skyrocketing until they become impossible. So process control in the manufacturing world, the way I think about it is stabilizing feedback. So here I have a ball and plate controller as an example. You can see how this function works. So this ball has a circular motion it's doing, and the plate is making fine grain adjustments to stabilize that pattern of the movement in a circle. So think about process control as stabilizing feedback. So we want to map this over to the software world. Imagine your brain as a stabilizing feedback system. So in order to apply the mathematics from control theory, we require a way to measure deviation from some kind of optimization target. So imagine I've got this flow of input information, then I've got this optimization target, a chaos signal, and then a feedback observe and adjustment loop. And to make a control system, I'm trying to make stabilizing adjustments towards some target. So let's break this down a little bit. So what is idea flow? How do we map these ideas? So idea flow is the process of communicating an idea according to an intention and validating that the idea was understood. So an intention, imagine I've got some idea that I intend to communicate, and then I put this idea on the wire, and I want to know if that idea makes sense to this person. So I listen to the feedback signals, and then I'm going to steer and make adjustments until I get that idea into that other person's head. And it works the same way in software, right? We've got an idea that we intend to communicate, and we're trying to communicate to the software, and we're listening to feedback signals in terms of red and green bars, making adjustments to communicate that idea. So from a process control standpoint, we can kind of think of it this way, as we've got this process output that we're listening to, this target intention, and we're making steering decisions to kind of dial in that thing that we're trying to accomplish. So an intention characterizes the goal that the system flows toward. So the way that I think about an intention is like the empty box that you're defining, and I've got an idea seed that I start with, and then I grow the idea to fill out this box. Does that make sense? Okay. So what is friction? Y'all seen this cartoon? the only valid measure for code quality is WTFs per minute, right? So when I started thinking about this idea of WTFs, what is it I was really measuring here is the time between the WTF and the yay moment, right? So friction is this time to recover our understanding when the observable behavior doesn't match our expectations. It's a TTR metric. So friction measures the frequency and duration of this confusion state, okay? So if I put this in terms of process control, so in a lean manufacturing context, in this case I was working in semiconductor industry, so we have a wafer that we were manufacturing and a target thickness that deposited layer was supposed to be. And then if the layer was too thick or too thin, it would be above or below this control line. And if it was too thick, it would be out of control. And the idea with process control here, dialing that in, lower variability equals better control. So if we map this idea to software development to this idea of flow control, you can kind of think of that target line as our understanding being in sync and out of control being this confusion limit. So if you have a WTF moment that takes longer than 50 minutes to resolve, that's like a conversation-worthy event, right? Let's talk about what made troubleshooting take so long. And the same idea applies here. Lower variability equals better control, right? We want to write our software and work on communicating our ideas in such a way that these problems don't get away from us, right? That we don't spend hours and hours troubleshooting. We want to maintain and sustain our understanding of the system. So the way I think about this is like a conversation with the code, and I use this technique of idea flow mapping, which I think of like a conversation sequence diagram. So imagine yourself having a conversation with a computer, and you've got an idea in your head that you're trying to get inside that computer, okay? So let's explain the idea to a computer. So imagine you're saying, okay, to calculate factorial, we want to multiply all the numbers together up to that number, okay? And our computer says, okay, I compiled. Okay. Then we want to run a test. Running a test is like asking your computer a question, right? What's the factorial of 4? And our computer says 6. That's not quite right? Well, how did you get 6? So we start looking and investigating the code, and the computer answers, okay, 1 times 2 times 3 equals 6. See the problem, right? We've got an off by 1 error here. So we fix it. Now we're communicating more information to the machine, right? I meant to include the 4, and then we run a test again, ask the computer another question, what is the factorial of 4? And we get 24, yay, okay? We communicated the idea. So imagine this little conversation that took place. Now, instead of paying attention to whether the bars are red or green, pay attention to the state of the human, okay? If I think about these things as these color-coded states, where at first we start the intention, then we hit that WTF event, and we're confused basically until we get that resolved, and then finally we finish that intention. So you can imagine these bands of time as these different states that the human is running into. So this is what we were mapping with those techniques. So if I think about then an idea flow network, I've got several people on my team collaborating on this software idea sculpture and working together to move the software towards some kind of shared intention. So from a systems perspective, I can imagine each one of these little people is a flow engine, all working together to move the software toward the shared intention. And friction is in these communication wires. We can think about friction as a percentage capacity of waste that is relative to that movement. So if we're not moving, there is no friction, okay? If we're not moving, we're not changing the software, we don't experience any of that pain. So the friction is relative to our intended movement. And the way I think about flow is the capability of the system to evolve an idea sculpture toward a shared intention. And this gives us a model for how we can apply mathematically these ideas of control theory to software development. And in this context then, human understanding is this ultimate constraint. So you can imagine this curve here is our WTF stress curve. And our goal here is to improve the quality of decisions so we're making better steering decisions and staying away from that line, right? We want to keep difficulty from getting too far out of control. And if human understanding is the ultimate constraint, then WTFs are the ultimate metric. So we want to think about these a little bit different here. So friction measures the frequency and duration of the confusion state, is this TTR metric in the context of idea flow. Okay? All right, so finally, how to science with paper and pencil. So first I want to talk a little bit about why measuring WTFs is important right now. So, microservices world, is anyone on this bandwagon right now? Okay. So we live in this new world where 90% of our software is made of third-party parts, right? We don't build anything from scratch anymore. We're like integrators, right? And instead of this complex procedural code with a bunch of nested ifs and things, what do we do now? We hand over our main execution thread to some platform, and then we write thousands of these little pieces of code, and then we wire them together with some magic configuration things, okay? And then what happens? We've got this whole new set of problem where we've got these skyrocketing diagnostic difficulty that's all in the integration space. We took all these problems that were, inside the boxes and shifted all the complexity to the wires, right? Anyone spent days, weeks even troubleshooting a problem with some one-liner magic code and trying to figure out their way through some complex mess of configuration things and some weird error message on the screen, and you go to Stack Overflow and there's nothing there that's current and you don't really know what to do because you can't Google the thing? I mean, there's so much hard in the world right now. And here's the thing. Our code metrics we use these days are almost completely out of alignment with where we're experiencing pain. What's the cyclomatic complexity of one line of magic code? We've eliminated all these problems of cyclomatic complexity. All right, good for us. We made that metric great. We just shifted our complexity and all of our problems and pain to this place that we aren't even measuring now. And I've seen so many projects go down this microservices road and end up with a whole new class of problems, a whole new class of expenses. And it's just kind of insane. Then you start looking at this reactive streams world. Isn't that exciting, cool stuff? And I watch people debug these things. And it's insane watching people copy variables out of their debugger, put them in a text file, so they can see what's going on, trying to trace the state. Like, it's ridiculous what we go through these days to debug these things. Human limitations are our ultimate constraint. So I think it's really important these days for, even if you do it for a short while, to spend a little bit of time to figure out where your pain is coming from, where your WTFs are coming from. And then we need to focus on changing our everyday habits. And the easiest way I've found to do this is with a simple process I got out of this amazing book, The Checklist Manifesto. Another one to add to your list. But a simple checklist of questions you can do a lot of amazing things with. So let's call this process science-driven software development. Okay, so we've got simple process here, simple framework, a strategy walk. We measure our WTFs, a reflection walk, and then we'll work on optimizing our flow. And this feedback loop is basically refactoring our vocabulary of patterns and then making a commitment to focus on the highest leverage 20%. So, checklists. So I broke this out in 3 steps. First, talk through the risk factors before the task. So go on a strategy walk, take one of your peers with you, walk around the building, and ask these questions. First, what's the goal of the task? What are we trying to do here, right? what changes will be the most mistake prone, and what changes will be the most difficult to debug. So I'm asking about both axes on that risk matrix, right? And then after you talk through the risks of the task, what can we do to mitigate those risks? Let's think about strategies for mitigating that. So have a little conversation, load your brain up with all these ideas, and then go sit down and do the task. And your brain will kind of be churning on all these things in the background. All right, next, write down WTFs during the task. Jot down the start time, take a screenshot, write a note in Slack, any way you prefer. Jot down the end time, and then keep notes on any unexpected behavior and clues as you diagnose the cause of confusion as you work. And then to get the metric, you have to do something really complicated. Subtract. Okay? Right. In our general rule of thumb, anything that takes longer than 50 minutes is discussion worthy, and don't worry about all the others. Then refactor your decision habits after the task. So this is a reflection walk. Same process, checklist. What were the biggest WTFs during this task? What made troubleshooting take so long for those? Just have a conversation about what those causes are. Start looking for patterns. Then I break this next one up into two sections. So what decisions would you make differently if you could do this task again? So imagine a hypothetical situation where you could rewind time and do the task all over again and try and solve your problem in the hypothetical case first. And then after you think through that exercise, then ask, okay, well, what could we do to reduce risk on future tasks? I found that separating these two things makes it much easier to come up with good insights for improvements. And then as you start working through these things, you start putting together a WTF knowledge base that is specific to the sorts of problems that you run into on your team. And that's basically it. And start working on making improvements. Remember, the hard part isn't solving the problem, it's identifying the right problem to solve. And one of the neat things about this is this idea of escalating risk works at every level of abstraction, whether you're talking about you as an individual, your team, your organization, community, or your industry. And it really unlocks so much potential to be able to do really neat things with these sorts of metrics. And you really start to realize that visibility changes everything. Like, imagine what we could do if we had real visibility in software development. You start thinking about what I'm doing at Dreamscale. So Dreamscale is an industry collaborative learning network. So I quit my day job a couple years ago to be a social entrepreneur and focus on building a platform for the people. So we're going to be pioneering socio-technical science. So if you're interested in upping your software game with a bit of scientific rigor and want to learn how to optimize flow and measure and systematically reduce your WTFs, we're going to be learning how to do this together as a community. And we've got this pretty amazing platform we're building, targeting our first pilot release in Q1 of next year. And then rather than open source, we're doing a membership-based model and pooling our money together to support a core development platform for this cooperative. And then we're building dream teams and dream organizations and learning our way there together. So if you're interested, you can sign up at dreamscale.love. Thank you.